This is a circle. That is a circle. This vertical and horizontal is smaller than that vertical and horizontal.
Draw the circle on the top left.
So we're going on to the next subject now. The next subject,
right?
The poll that won was observations, yes. So for the next hour, we'll be talking about observations.
Okay, I'll probably do better with observation.
Oh, yeah. And how did we get off of Foucault's on the Cavendish? I just didn't see the transition there. I didn't get it.
No, because it came to the end of the hour.
Yeah, it's the next hour.
Yeah.
Well, he went from talking about Foucault's pendulum on the last hour to Cavendish.
Science. Yeah, what is science? It was supposed to be science.
Yeah. Everything's science.
Okay.
And now we can go to observation. Well, I guess, do we observe curvature?
No.
Oh, okay. I'd say that we do. Yeah.
Okay.
Did you have on the horizon?
One? Oh my gosh! I almost left. I almost exited out of livestream.
According to Craig, you can observe gravity right behind me.
I was just saying that I left when you left your seat, so you've got lots of gravity behind you there.
There's a shitload of it. I'm going to bottle it up and sell it.
Okay, so you guys can take your votes for the next third hour's topic. We have Satan's Little Season, Biblical Cosmology, Trinity, and Gas Pressure. So there's for the next offer. For this hour, we are talking about observation. So far, Luca thinks there's curve. We told him no, there isn't, and he's given up. So
that was quick. Yeah, that was easy.
Hey. Then what about the high? If you go high enough up, the horizon will drop.
You go high enough up, the horizon will drop. Okay.
Yeah.
Well, what is the horizon, first of all, Luca?
High altitude horizon drop. Yes. The horizon is where the sky meets the land.
Appears to meet the land. It doesn't physically.
Appears, yes. Appears.
So it's an optical effect.
You could say that the horizon is optical, yeah.
Okay, so you do understand with optical effects, with distance, it can cause a difference in what you perceive on that optical effect, correct?
Like it gets smaller because of the angular size? Is that what you mean?
Yeah, my point is with distance, optical effects seem to change perception. They look different. They look optically different. They look optically different with distance.
But like, no matter where you are on Earth, as long as you're like at sea level, the horizon will be the same distance away from you always.
Ah, so there's no such thing as black swan refraction.
Well, yeah, of course that's refraction. You get what I mean.
Of course.
You do that.
Hey, Luca, how tall are you?
I'm 160.
160 centimeters? What's that?
Centimeters, yeah.
Okay, see, I'm taller than you. I'm taller than you. Okay. How come my horizon is relative to my eye level the same as you?
Well, actually,
it didn't lower. It didn't lower. It's the same. It appears at the same place relative to eye level.
You think you'd be able to notice that?
And for you, but my horizon is further from me than yours is. Why?
Because you're taller.
Right. Well, if it's physical, then why would it be further away?
Well, it's optical. I said that.
There you go. So it all depends on your elevation, right?
Well, yeah, pretty much.
Okay. So I've been up as high as 8,500 feet on a mountain, And I've looked out across the valley and at the other mountains, and I still don't see the horizon is still right there at the same place it was when I was on the ground relative to my eyes. How did that occur? Why didn't it go down any?
Or do you think you'd notice
Yeah.
that it? Well, you'd first need to measure it at ground level and then go up and then measure it again when you're up there.
Yeah.
To really notice it.
It's in the same spot, man. It's in the same spot. I can just see further.
Well, because mass attracts mass, then the sea and the sky must be attracted to your eyeballs, so it's lifting up your eyeballs as you go up the mountain. You know? It's got to be it. It's got to be it.
Oh shit!
Look, if you're up about 8,500 feet, the amount of curvature you'd probably be able to see would be like 2.2, maybe.
Is that based with refraction or without refraction?
Well, that's on an average day, so I guess the normal amount of refraction, I guess you'd be able to.
So what would happen if we have to take refraction away? Would it give a different observation?
If there was no refraction, then you'd have a different observation, yeah.
So we always only see the optical apparent horizon, correct?
Yeah, basically.
So not physical curve.
But it is physical curve.
How?
Where? You don't ever see it.
You observe. You just told us you observe only optical. So how is it physical?
Yeah, you observe optical, yeah. Yeah.
So we have optical curve, not physical curve.
That's so Earth's too big to see
the
curvature.
But since the Earth absolutely curves, you.
How? Where's you proving that? You just told us it's optical, so therefore it's an eye trick. It's not physical.
The horizon is. There are some circumstances where I think it can be physical as well.
It has to be physical on a globe.
It's a physical line where where a sky meets the ground.
You just said it was apparent.
Yeah, it's an apparent line because of refraction, because of the atmosphere.
I got a question for you.
Always be looking through atmosphere. It's optical, but it is a physical line as well.
Do you see Saab's background here? You got behind him?
Gravity.
Okay. All right. Yeah. Where gravity is. How far away is that sun away from him? Do you know?
About 93 million miles.
How did you come up to that figure?
Yeah, that's what they say.
They? Who's they?
The physicists, astronauts, scientists.
Hold the phone here.
The astrophysicists.
Astrophysicists. That's Disneyland. Okay, that's not real. Okay, here's the physics that you have. You have actual physics. Okay, we're not talking about theoretical physics. We're talking, how did you get that distance to the sun? That has nothing to do with, what was the science involved with determining this 93 million miles that's changed since Copernicus from 3 million. It's actually gone up 100 million and then back down again.
Of course it changes. Of course it would change over the years.
By 100 million miles?
Yeah.
How?
Because we had an absolute, because back in the day they didn't have all of this equipment. They could
What equipment?
Like radar.
You can't check the sun. You can't measure the sun with radar.
They didn't have back then. So of course it would be radar. Millions of miles.
What has radar got to do with anything?
Well, you can measure the distance using radar.
No, you can't.
It's a black body.
but it's got a big enough, it's got a great enough density that it bounces it back.
No, it
It's a
doesn't.
black body. Well, it's claimed to be a black body, so it can't. It
You also
absorbs
have
all
to
that helium.
You have to also consider at the orbital speed the Earth is supposedly going around the sun, and the fact that it takes about 8.5 minutes for the signal to even reach the sun, as it attenuates, and then supposedly, according to you, bounces off of the sun, still attenuated, and it attenuates even more back for another 8.5 minutes. Okay, spreading the signal out, spreading that uses the inverse square law of light, at which point the Earth is now moved approximately 18,000 miles out of position from where you sent the signal from.
And it still appears at
So
the
it's
same
going
place.
to bounce back to a location that you were not at anymore.
Remember,
so that won't work.
Yeah. Remember that the Earth alone at the equator moves around at 480 meters a second. Now that's just the rotation. Then it's still the Earth as well moving it around its orbit, which is what, 66,000 miles an hour. It's like crazy.
But they can predict where it will go. Yeah, they don't.
Yeah, it'll go back to where, if it actually comes back, and if it were actually possible to send a signal that far, it would be 17 minutes before you got a return signal. Figure out how far the Earth has moved in its orbit around the sun in 17 minutes, and it's about 18,000 miles, man.
You know, it'd be an interesting demonstration if a Globie can do us a favor. Take a dartboard and try and take a BB gun and try ride on a horse or drive in a car as fast as possible past it, shoot the bullseye, and see if it's going to bounce back to you.
Yeah.
Because that's exactly what you're claiming is happening when you take radar to the sun.
Right.
Hang on, do I have that video? Where's that one? Throwing a ball on a...
I've heard how they supposedly do it, and they register like the concentrated heat or signal from that to determine where it is, which they can't hit it with a radar necessarily. It's not just they don't directly aim a radar at the sun and don't work right. It won't. They do a radio telescope is what I understand. They use antenna to collect data from it. But it's not a radar signal they hit it with. They don't ping it with a radar. No.
Yeah. I just want to point out. I just want to point out how dumb people are. I thought the Earth moved 1,000 miles an hour. Yes, the Earth rotation is 1,000 miles. Sav is talking about the Earth's orbit around the sun in Muhu.
Minute.
Isn't the sun rotating around the center of our galaxy at how fast again?
Different speeds and vectors. Everything's going in according to your heliocentric belief.
Yeah. We're just in
that's
one of the little.
Yeah.
So true, Eugene. So true.
That's interesting. Yeah.
Yeah. What's interesting?
We measure the sun's distance indirectly.
And what does indirectly mean?
Yeah, let's see.
It's calculated, in other words.
Calculated, exactly.
So it's calculated, not measured.
Nearby planet, time they echo, and use celestial mechanics to convert that single precise baseline into the astronomical unit.
The AU units, yes.
Yeah. It's a brilliant blend of a simple stopwatch, physics, and orbital geometry. No need or hope to hear a ping back from the sun itself.
Whoopsie. So you don't need to hear a ping back from the sun itself. So it's assumed, it's calculated, and accepted by affirming the consequence based on no evidence whatsoever.
But if we can calculate the distance, and why can't we use the calculation?
Can calculations be wrong?
I suppose, yeah.
You know why the sun's distance has changed throughout all the years?
Because we didn't have the precise enough tools to measure it?
Because it's all calculated. It's never measured, Luca.
They
Based
just said
on
they
the bloody
don't.
estimated size of Venus.
Yeah.
It's ratio based. What's an AU?
It's like
Astronomical
using a-
unit. Do you know what astronomical unit is, Luca?
No.
It's just a unit measure given in astronomy. So it's
okay.
it's to give a very large number, in other words.
Okay.
It
And
could be
that
anything.
1 million is a large number, so.
It's a guesstimate, really.
Big
They
guesstimate.
can, yeah.
Stretchy guesstimate.
Oh, where is that? There we go.
What?
There we go.
Ball. Watch this. And he's on a. They're on a.
On a rotating.
Yeah. It's like a little.
This would have worked with the Coriolis when we were earlier with the science, yeah. But I guess this can still fall under observation, because you don't observe this in reality.
Let's see.
Make the bucket. Make the bucket. Yeah.
Oopsie, he must be drunk.
Football.
No, imagine he's throwing that ball while he's also spinning in that chair.
Look how it's going to appear to curve, guys. Remember, he's throwing it straight.
Mm-hmm.
Yeah.
He's coming straight from the position he was in.
But isn't that
He's
exactly
he's only appearing. He's only appearing to rotate underneath, correct?
But isn't that exactly what we observe?
In physics,
So,
yes.
If we observe what
Not on
they're
Earth.
observing,
That's
and
not what we
they're
observe on
spinning,
Earth, though. We don't observe that on
it's
Earth.
exactly what we observe on Earth.
No. Demonstrations like that we observe. You can demonstrate Coriolis effect, but we do not see that.
When do
Yes,
you see an airplane zooming away
When
from
we
you?
fire bullets.
I've shot many bullets. I've never seen that happen.
If you,
I don't know, Solve.
if you-
Last time you shot your rifle, have you had to account for this beloved observed Coriolis that they're talking about?
Nope. I'd never even heard about it until as people was talking about it in Flat Earth, and I was like, "What the hell you been talking about?" I've been shooting all my life, and I ain't never took that into account.
Odd. That's weird.
Yeah, but like, Sovereign, have you ever needed to take it into account?
Why would I? There's nothing moving. It's
So you wouldn't. So you
ridiculous.
There's
don't
one
need
thing
to
you do take
it
into account,
so you-
Luca, that's actually
so-
more than anything else, and that's
well.
wind
Yep.
and your angle, your elevation angle.
Yep.
Wind won't. Wind. The thing about wind is that it changes often.
That's right. Yeah, there you go.
So we don't.
Wind
really
100 meters away from you can be different than 400 meters away from you.
That's why you observe the effects from you all the way to the target. Okay? There's indicators, grass, leaves, and they'll give you an idea as to how fast the wind is going and in what direction.
Yeah.
So, Saab, you
don't look up in the sky, see a plane deviate, and decide to shoot in that direction or whatever.
No. I've never seen planes deviate in the sky neither, but Saab, have you ever shot indoors before? The question? Have you ever shot inside?
Yes.
Okay. Did you had to account for Coriolis inside when you
No.
were shooting? Oh, man. You would have to if the Earth was spinning, though, right?
Well, I don't know. Airplanes don't have to account for it, and they go a hell of a lot slower than an airplane.
Mm-hmm.
You know, I'm trying to figure out how an airplane take off at the equator that's supposedly going 1,040 miles an hour and head due north and not have to keep adjust his east-west orientation at any time because of the change in rotational speed of the Earth as he goes north.
Yeah. And
There
then
you go,
when it
guys.
lands with that landing gear, and the landing gear doesn't get spiked out from underneath it, you know.
Hold on. We're flying backwards now. Hold on.
Oh my god.
That's what you observe, correct?
No.
Well, that's what your globe claims has to happen.
No. The
Yes.
plane has that momentum of the Earth already.
I mean, it's quite the opposite in some in some aspects, because sometimes with parallax, you don't see the planes moving at all, depending if you're in a car or whatever.
Momentum?
So sometimes you see the opposite of what
Okay.
would be
The
real.
conservation of momentum?
Now I'm going to blow Luca's mind.
One
Because now
plane
there is
will
really
take
one
off,
showing.
they
Look,
cancel the
look,
momentum of the Earth with them.
look. What's going on? Why is that
Yeah.
plane flying backwards?
It's obviously edited, so no.
No, it's
I
not
can
edited.
tell you why it appears to be flying backwards, Luca.
The plane
Because
you're in
someone
goes
is flying higher than him, recording him, flying
and going
faster.
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 Ah. So don't they both have the
Yeah,
momentum
parallax.
of the Earth?
Yeah.
Parallax.
Now, why is the one
He's
going
flying
backwards and the one
faster.
isn't?
Yeah, that's right. Yeah,
So why is one going backwards and the other one isn't?
because it's
Yeah, if
flying
you
faster.
go- No, conservation of
You-
momentum. That's what he just
You
said.
said it was
That's why he
flying
said it.
faster.
So conservation of momentum is not a thing when it comes to Earth rotation in planes.
Can things go faster than other things?
You're not getting
I've
what
seen
you're saying.
cars go faster than other cars. What? Cars can go faster than other cars by speeding up.
The
So
point
why
is they're
can't
both
planes
supposed.
go faster than other planes by speeding up?
You said planes can't fly backwards.
We observe
trying to show
it,
you
too.
it's an
That's not
observed
actually flying
phenomena.
backwards. It's just that this plane is flying faster than the other plane.
Can
So
you?
it
So it's
appears
not
to be
Earth
flying
rotation. So it's not caused by Earth rotation then.
What?
We
How
observed
can
the
you get
plane
that?
fly backwards. We observed the plane fly backwards.
Because the
So-
other plane is flying faster.
So not Earth rotation then.
Yeah, there's an old example of it.
It's
With
going
like
faster. How's that got anything to do with Earth rotation?
I'm
he's
just
messing
pulling
with
your
you.
leg, Luca.
Well,
Yeah. So look, you're on a runway and you take off going west, and you get to 500 miles an hour, and the Earth's rotation is what at the equator? It's where you take off.
you'll have you'll have the 1,030 miles per hour that the Earth is going, take off going your speed, and your speed is added onto that 1,030 miles per hour that
but
you were already going before. So you've got a cumulative speed of about 1,000 for 1,000, like 1,700 or whatever speed planes go. You'll have that accumulated onto the 1,030 miles per hour that you
Well,
were
what about going the other way, Luca?
Yeah,
what about going the other way?
Yeah.
If you're going the other way, you're only
take
doing
off.
average speed of about 450, 500 miles an hour. Let's put it there to make it easy, okay?
If
So
you
let's suppose the
if you take
airplane's
off
going 500 miles an hour, and he takes off going the opposite direction of the Earth's rotation, right? Which is 1,040 miles an hour. You just said that it adds to it going in the direction of the rotation. Now going in the other, it's only minus and back.
Yeah.
So now you'd actually be traveling backwards, or the Earth, the destination would come up behind you. You'd never catch up to it. So if what you were
wouldn't
saying
be
is
traveling
true,
backwards, you'd just be traveling slower.
but what about going?
If two
Okay,
planes were to
Luca-
take off in completely opposite directions, then one would appear to be going
Okay.
slower than the other.
Okay, let's say you jump in a raging river. A river's flowing, and you jump in there and you swim. And you're swimming as fast as you can against the current.
Yeah,
What's going to happen?
you'd get swept backwards.
So you're swimming forward, but you're still going backwards, correct?
Yeah, because the current is way stronger. Well, it depends on how fast the current is.
So let's say
if the current's slow,
wait. No, that's fine. So let's say you turn around and you swim as fast as you can with the current. Will you
Yes,
be
you'd be
swimming
going
faster than what
Yeah.
you did the other way, the other
yes,
direction?
you'd be going faster. Look, I said that one plane would be going slower than the other, and if they took off in opposite
It would be
directions.
dramatically slower. Dramatically slower.
So my question
No,
again is: would
really.
the Earth would it not be more viable just to fly in the opposite direction just and wait for the Earth to come to you, you'll use less fuel.
Yeah, but whose perspective are you looking at? If you're observing it from the outside, that when you go against and with the current,
Yeah, but that's a physical thing. With and without, if you're going against or with the current, that's a physical thing. That's not an optical thing. That's a physical thing.
I had a real life example like that, Luca. I'll give it to you. I was down in Tempe, Arizona, and I climbed this fence. They had reservoirs, and they got these water canals, and I fell into it. And it's going about 40 knots. Literally washed me downstream. And if I would have gone with the current, I would have went under a bridge through a turbine and probably been killed. But I swam against it eventually, but it took me a long time just to even get momentum to go forward. I was just treading water the whole time.
I've done that, just staying in the same place in the sea. Yeah, it scared me.
Yeah, that's what we're basically talking about. There is a medium above us that they're flying through. They would actually maintain flight if the Earth was moving. You could actually basically hover there. Just wait for Paris to come along or whatever city you're going to.
If the Earth is underneath you spinning faster than you're actually moving, then you might as well wait for the country to come up behind you.
Yeah, that's physical. That's what we're talking about. Not an observation. Yeah. It's a physical thing, dude.
That's not how it says it works.
Who? How?
You can't just hover a helicopter and just wait for the country to move beneath you.
Yes, because the Earth's moving. We agree.
Yeah. You're saying everything's tied down. So gases and wind and stuff don't move physical objects, right? It's just kind of like this is a big blob of air attached to the ground. How does that work?
If you somehow got the helicopter to, have a hypothetically, if you somehow got the helicopter to be moving constantly and have a lot of fuel in it, then I suppose you would eventually see that the Earth rotate beneath it.
Okay, let's put it this way, Luca. Do you believe that the Earth's atmosphere is velcroed to Earth?
What does that mean? Just held down?
Yeah, like moving with the Earth rotation.
Lockstep,
the atmosphere would, yes, it would be moving with the Earth rotation. Yeah.
So why do we have wind then?
Wind is caused by pressure differences and heat differences.
Yeah, but then it's not in lockstep.
But the wind isn't really in lockstep. No.
Is air bonded?
Well, if you look at it as like one giant atmosphere, then are you saying that? Well, yeah, gravity wouldn't really affect each individual.
No, I'm not worrying about gravity right now. I'm specifically talking about behavior of gas. Let's put it this way. If I swish my hand through the air right now, if we use the Schrodingian effect and I swish my hand through the air right now, you would agree that air is not going to, with my hand, it's going to vortex around and go the other way. It will stay behind. My hand's just going to go, but that air is going to stay where it is.
Are you talking about
so it's not going to move with my hand?
Of the air that you swing arm through, or each individual molecule of the air?
But that's how air is. Air is individual molecules.
But we look at the atmosphere as not individual molecules, as one entire thing.
But that goes against gas.
Exactly.
You muted, Soph.
You can't obtain that without physical containment because of the fact that they're not bonded together. Okay? They're all individual. So they're not, it's the only way to have a mass of any gas or gases is to have it physically contained.
And SKS is bringing up exactly what I wanted to ask as well. So at what altitude atmosphere is not moving in unison with the ground beneath it?
Well, when you, the atmosphere is pretty much always going to be, unless you go really high and there's like no atmosphere left. Because
Right. So when we have high altitude balloons, at let's say 100,000 feet, there's hardly any atmosphere. You agree?
Yeah.
Why are they still moving with the Earth then?
Well, they're still either they're like moving, they've got conservation of momentum and moving because of the speed that they already
Do you know
had.
do you know how tangential velocity works?
That's the speed that Earth has at the crater.
No, the tangential velocity says the further away from the radius, the faster you'll have to move to keep up the same rotation.
Yeah, and the Earth spins.
So
about
let's, for instance, take observation of Felix Baumgartner then. How high was Felix Baumgartner? 200,000 feet?
No.
220,000 feet?
Wasn't it 100?
Yeah, it was about 220,000 feet or something.
Was it the Red Bull jump thing?
Yes. Why is it that the Earth didn't rotate under him?
Did he feel any velocity while he was up there too at that radius? He would have to, wouldn't he? It'd be immense almost. If he was
Felix Baumgartner demonstrated there's no rotation of Earth whatsoever.
But he had he had some of Earth's movement because of the conservation of momentum. At
220,000 feet where there's no air.
He was still moving. He still had the conservation of momentum.
So how did he pick up more energy? Wait. How did he pick up more energy? The higher you go, the more energy you have to conserve. In other words, you need more energy to conserve that rotation because you have to speed up. So where is he getting that energy from?
What? If he was...
How is he gaining energy to rotate?
He isn't.
Exactly, because the Earth's not rotating. That's the point, Luca.
He was losing energy, sure. Because the longer he stayed up there, then the conservation of momentum would eventually run out.
And how long did he stay up there for?
The descent time was about 9.5 minutes. So
9.5 minutes. Do you know how far Earth would rotate under 9.5 minutes?
Oh shit!
He would literally be landing in the ocean.
But
somewhere in the Pacific,
momentum. It would. The conservation of momentum just doesn't run out instantly as soon as you leave Earth's atmosphere. You'd still have it. It would run out eventually.
It's not indefinitely.
Sure. But and since it's going back into Earth's atmosphere, which is also rotating with the Earth, then he'd gain the momentum back as soon as he hit the atmosphere again.
Okay. So let's say Felix Baumgartner was here. Okay. Let's just this is like the closest to the Earth. Now he's going up. Let's say he's 50,000 feet. Now he's 100,000 feet. Now he is 220,000 feet. Okay.
Mm-hmm.
Correct. Now
220.
Yes.
I thought the altitude was around 40.
Huh? No.
As far as I know, just 220. Let me get it quickly. Make sure.
Wasn't it like 40,000 meters or something? Oh, right, feet. You're saying feet, not meters. Okay, gotcha.
Feet, yeah.
Feet is
wait.
Okay.
No, I wasn't 200. It was 130,000 feet. Sorry, guys. I misspoke there. Why did I think 220? Anyway. Yeah, it was 128,000 feet. So that's 39 39,000 meters.
39 kilometers. About that. Right?
Okay.
Yeah. I think that's right.
39,000 meters.
And
Yes,
they advertise it as a
yes.
jump from space, Luca. They jump from space. That's what
Yeah,
they say.
because
39,000, yes.
because they claim 60 kilometers is space. But the point I'm making now, Luca, is how long did it take him to get up there? A few hours?
It depends how fast the rocket or whatever it was using was going. If it was a well designed one, then it could take like maybe 15 minutes.
It was a balloon.
Maybe 20.
It was in a balloon. It took him 90 minutes.
90. Oh my. Okay.
He lost a lot of momentum in that 90 minutes, I'm sure.
So
the atmosphere is moving with the Earth. So.
Okay. So with 90 minutes to get to 130,000 feet, okay?
And according to you, that they say space doesn't actually start until 60 kilometers. So he didn't actually leave Earth's atmosphere.
He couldn't. He was in a balloon. Nobody can leave Earth's atmosphere.
Yeah, obviously.
Nobody can.
Yeah, otherwise the balloon would pop or something.
Yeah, let's just say this is 70,000.
Well, no, it's enclosed. You're not getting out.
It's contained. Yeah.
Otherwise, you wouldn't have that volume of gases in order to rise up.
And let's just say this is 5,000 feet, whatever. 500, 5,000. Okay.
Obviously, it would be a helium balloon for him to
get
up that in that.
Okay.
Sort of.
So let's say, at 5,000 feet, you're saying he's still rotating with the Earth at 1,080 miles per hour.
Since the atmosphere is quote unquote Velcro, you said, to the Earth momentum. So,
well, Luca, if that's true, though, if that's true, that means that tangential speed of that air that he's up there in is going many times faster than it was at the Earth where he took off from. Correct?
Mm-hmm. That's the point.
What?
Hello, everyone.
How would you speed up when you go higher?
Well, because they have to keep up with the thing. When you get concentric circles, they have to go just like a record, man. The edge of the record, the outside edge, is traveling much faster than near the middle.
Mm-hmm. Because it's more distance to take. Remember, the more distance you travel in the same amount of time means your speed has to be increased.
It would take less energy the higher up you go because there's less atmosphere.
But you have to travel faster, correct?
No.
Why not? To go travel a further distance, you don't have to travel faster.
You got to keep up with the momentum. Go ahead.
If it's less denser, you have to provide more energy to push from something. So yes, you have to go faster.
In order to escape the Earth's atmosphere, you would need you would need like lots of energy.
Yeah, you can't get through it, man.
And I'm not talking about the dome. But I'm talking about from my point of view, gravity would be preventing you to escape, right? So I'd argue that a closed system, you'd need a force to escape a closed system, right? You can't just escape it without a force.
You can't escape from a closed system, Luca. You can't transfer energy in a closed system. You can't transfer matter in a closed system.
Well, you can transfer energy, you just can't transfer matter.
Yeah, matter, yeah.
So you need energy to escape it, right?
So quickly play. I'm going to play like 2 minutes of the screen, not even. Just quickly watch this, Luca.
If you can do that. All right, so tangent velocity notes. Uniform circular motion is the motion of an object with constant speed, not constant velocity. The reason the velocity is not constant is because the direction is always changing.
Do you understand that?
Are you talking about the orbits? The many orbits?
No, this is talking about the same thing. Felix Baumgartner going more up. The higher he goes up, the faster he is going to have to speed up to keep with the speed of the rotation of the Earth.
The Earth's
changing velocity.
Yeah. The Earth's rotation is constant there.
No, but it changes vector.
For him
constantly.
to keep, it changes vector constantly. Is correct. So when you're claiming, he's going up and he's keeping with the rotation of the Earth, that means he has to literally speed up to keep up with the rotation. So where is he getting this energy to speed up?
I guess, the balloon is made of helium, so it's a pressurized helium balloon.
Watch this quickly.
But it would obviously have to be pressurized.
Just look at this. Listen quickly.
Okay, so an electric rod has 3 light bulbs, which are depicted in blue. The rods, maybe I'm going to use a different color since that's blue. I'll use this green. Okay, the rod spins with the uniform circular motion.
Mm-hmm.
Light bulb A is the closest light bulb from the center of the rotation. Light bulb B is the furthest away and at the edge of the rod. Which light bulb takes longer to go all the way around? Okay, so this is going to go in a circle like this. Which one is going to take longer to go all the way around? Take your time, pause it.
None of them. They all go the same direction because they're on the same rod.
Mm-hmm. Well, you
remember, but you have to understand B is traveling a further distance than A.
Yeah. Well, yeah.
So which one is traveling faster, B or A?
B.
So more energy required for B, correct?
It's just that there's less energy pulling you back. There's less energy you have to go through. There's less like.
I don't think you. That's a different vector.
Let me make an analysis then. If you have 2 people going the same speed, one is at point A and the other is point B. Now, even though they're going the same speed, one is appearing to go faster, and that would be B. B is appearing to go faster than A because there's less.
Physically, they're going faster.
There's less drag in the way. There's not as much drag. So B would be going faster than A. It's not that he's using more energy. He's using the same amount of energy as A. It's just that there's less drag to contend with. Therefore, he's going faster.
But what happens if they move with the wind, with the rotation, Luca?
Well, if you're moving with the rotation, then obviously that's going to increase the speed a little bit.
And there's no difference in speed. That's the whole point. There's no difference at all. Based on a spinning rotational sphere, you're supposed to have tangential velocity change the higher you go up. You don't see this. And because there's hardly any air up at that altitude, it means there is no atmosphere to push you with the rotation of Earth.
That's right.
Isn't that how they say they develop orbits, supposedly? You get so high up they just fall around the center of mass over and over again.
Constantly.
How you get into orbit is you fly an angle. You don't fly straight up. You need to fly at like a degree angle, so you can get into proper alignment, I guess you could say.
They call it
straight up is an angle.
Yeah, straight up. If you get straight up and just
It's still an angle.
Your entrance.
It's still an angle, though. Straight up is still an angle.
Shh, don't say angle. He's gonna get triggered, man.
Bev's, oh, okay.
Well, if you're on a tangent point on a sphere, that would be an angle, right? So you're angling off that sphere. And especially
by the way, 15 minutes left till the new topic, guys.
Well, I got a great example that P-Brain did just recently. He got a new video out about exactly this topic almost.
Oh, you want to put it up? Because you got 15 minutes.
It's in private chat right there. You want to grab it?
Private chat.
There you go.
Oh.
Yeah. Okay,
this one.
Shout out to P-Brain, by the way.
P-Brain. Yeah. Get ready for guitars.
Is it green water moves to the credit my spinning ball? Oh, okay.
Oh yeah. This one is this. Well, you're on about the water. He's on about the water, like with the spinning. The water should be going all different directions. Is that?
Yeah, it should.
Yeah. It's a good video. It's a good video.
Yeah.
Okay, here's a little demonstration how water moves to the equator of a spinning ball. Here's my trusty blue ball, and I have some latitude lines drawn on it. So this latitude line where I have this little green drop of water is about, I don't know, 50, 55 degrees north latitude. Okay, so you'd have hundreds of mile per hour moving water, which wants to move straight. The ground is being forced to turn by nature of a sphere. That line, which critical think that looks straight, all you have to do is look at it at the right angle. No, the right angle is to look at it from perpendicular to the surface, because it's a sphere. See, they thought and they described it as a cylinder. This is how they made their sphere work. But the fact is, all points on a rotating sphere are forcing you to turn on the rotating sphere Earth, left in the northern hemisphere and to the right in the southern hemisphere, except for the equator. That you turn down and around the ball, like I'm demonstrating with these cars. But as you can see, the latitude line up here around 50 degrees north latitude is a turn, right? When I show the car moving straight, you can see it's not a straight line, right? That straight path the car is making is the path water will take as it separates from the ground and it migrates down to the south. And that's what I'm going to show you in this video. Because I actually had some ballers say to me, how do you know the water's moving to the equator? It's not. It's just lifting at the equator. And I said, all this water, like this red ball, all this water is being stored at the equator.
This video
and that's lifting off.
Interesting fact, I used this video that he's showing now in one of my videos when I started my channel. And I had to take it down for copyright issues.
Wow.
Huh.
These guys literally copyright me for this video he's using now.
That's strange. Why would he do that, man? To be honest. Yeah.
No, these are the slow-mo guys.
Yeah,
they copyrighted me.
Oh, the slow-mo guy copyrighted.
Yeah, they copyrighted me.
Unbelievable.
It was one of my first videos on my channel. So I didn't contend with it. I just took it. I was like, okay, whatever.
I thought they were all right as well. I mean, they're quite funny.
I love their content though. They've got really good content.
Got that camera as well that can slow it down to what?
Yeah.
250,000 frames per second.
Yeah, it's hectic.
Maybe more.
No, Dumbos. It's moving to the equator. Newton's law, which is just common sense and what we observe, things move in a straight line.
Yeah.
They don't want to turn. There's a force required to make things circle or turn.
And one other experiment we can do to show that a force inward is required to keep the ball moving in a circular path is to, at some point, as the ball is rolling around there, I'll just pick up the ring and watch what happens to the ball. The ball will be moving in this path. When the ball is right here, I'll lift up the ring and you'll notice that the ball will continue on with a straight line motion in the absence
because it changes
of a net force.
It changes vector. Whoopsie.
Demonstrating that a centripetal force or an inward force is required to keep an object moving in a circular path.
Right.
Like these latitude lines on a sphere. And that force that's forcing the ground to turn, and in this case it's a rubber ball, but on the Earth, the force is the sphere itself. And the ground being bunched up in its ground. You know, although they say that it was an equatorial bulge, there is an equatorial bulge and the ground shifted and moved, but it's in equilibrium And they may come up with some cockamamie story, but equilibrium just means that it's bunched up. It's moved, it's wedged up against ground in front of it. The equator is bulged up. I talked about that in this video, my last one I put up.
Yes, the centrifugal acceleration.
Table, please. Garlic bread's ready. I said the garlic bread.
The surface tension and, say, gravity as well.
Keeps it going in that circular motion.
Moves it towards the equator. Moves the water towards the equator. The centrifugal acceleration, the surface tension and gravity move water towards the equator.
All
Luca,
three of those forces. Yeah.
Luca, I hope one day when you're going to ask to marry your wife, you're not going to ask ChatGPT to say when you can marry your wife.
Set up a date, everything. Get ChatGPT to propose and everything.
Have
What
you
color
seen
flowers should I get her?
AI, literally, like AI girlfriend. Chatbot.
What you want an AI girlfriend?
No, I know a man that has an AI girlfriend.
Oh, you know him. Some people are
like that. I don't know him personally, but I've seen him on.
Some people are very weird.
Yeah. He proposed to it, didn't he?
A wife and kids.
Yep.
He's basically replaced his wife with an AI chatbot.
That's crazy.
I did a show on that. Yeah.
Hey, Flatfoot, I got an observation question for you. See what your response is. Why doesn't the sun measurably change in horizontal angular size?
It does.
Okay, can you pull up an example
We
of
literally
that?
showed it the other day for Luca.
No, you showed. Hold on a second. You showed it vertically. Can you show it horizontally?
Yeah, horizontal and vertically.
I'm going to show you why. I can show you why.
Okay, yeah, show me.
Real easy. Okay. So, put me up full screen for a second, Flats. Turn off my background so I can do
How many times do you have to explain this to them, though?
You see this thing right here? Okay. I'm going to extend my arm forward. I'm crooked at the elbow like this. I'm going to extend it forward. You see a definite change in size, right? You see a definite change in size.
Horizontal and vertical, yes.
Now watch. I'm going to go way
parallax.
Way back here. Now I'm going to extend my arm the same distance. Did you see much change at all? If any.
It changes a little bit. Yeah, it changes a little bit.
Not noticeable. Now, if I were to go back even further, the point is if something's already far away from you and you have a limited amount of time to observe it, in other words, if you could observe it from here all the way back to here, that would be a different story. But you're not. You're only observing it from here to here.
So are you saying that? Are you saying that the sun doesn't change? Hold on a second. Are you saying that the sun doesn't change angular size then horizontally?
Not in your view. Often not in your view. You don't. You're not able. You have to let someone finish what they're saying before you cut in. Okay. So it depends on the amount of time you're able to observe it as well. Okay.
So can you see the sun do that?
If you're high enough.
What about on the ground?
No, of course not.
Okay, so Flats, you don't have one where you see a size change.
Yeah, you.
Okay, so which is it?
Okay,
Sav, is it you can't see it or you can, Sav?
It depends.
Just a second. If you were to actually take screenshots of my before and after fact, you would see a small amount of change. Okay. Now.
Okay, so you would see change now. So you changed your story.
Wait a second. Listen to me. Stop looking for your gotcha because you don't have one.
Well, no, you keep changing your story.
You keep interrupting. You don't understand what I'm talking about.
Okay.
The lighter when I showed it to you in the distance was still changing in angular size, but the appearance of it changing was not there. You had to really, really discern it to look, as is shown in this picture.
You have to physically take screenshots. You have to take the screenshots and you have to lay them on to see. Can you see on the second the vertical and horizontal is different size from the
how
first
can you
picture.
tell the horizontal is different in that?
Literally, you can see it on screen. Are you blind?
Where's the horizontal difference?
Are you blind, Wesley?
Okay, you're saying on the right. How do I tell the horizontal distance is different?
Are you blind, Wesley? That is the new one. That's the old.
Yes,
Can
it's
you
much.
see vertical is smaller and horizontal is smaller.
Okay, how did you measure that the horizontal is smaller?
You can see it. Jesus,
you
can
can
literally see it.
You can.
Yes. You know what? I'm going to do it this way.
Why don't you do the same
Just
picture but do it horizontally?
Just
do the
for
same
Wesley.
picture and do it horizontally. Yeah.
Just for Wesley, guys.
it's in front of your eyes, for fuck's sake, man. Seriously.
No, but this is Wesley.
I won't take it from guys that say that.
Hold on, Wesley. Are you saying that if he turns that image on the right 90 degrees, that'll be enough for you?
The image on the top.
You're just looking for shit to waste people's time.
Yeah.
There we go. That's the new one.
That's not the size of the sun.
That's the old one.
You can't even draw it straight. That's how dishonest you are. Draw the.
Wesley, you're so fucking desperate. It's not even funny. Your desperation is
really dumb.
Draw a picture of this in the top left.
Your desperation is oozing.
Flash, draw a picture in the top left. Yeah, put that sun in the top left now. No, the one in the top left. Why don't you take a picture of it in the top left?
That is the top left.
What do you
that
think?
Big one is the top left, you moron.
Holy shit!
Why don't you do the whole sun in the top left? How hard is this to understand?
That is the top left, you moron. Look,
pull it up there.
It is the top left one.
Look how it's more horizontal than that. You
this
moron.
It's smaller. Do you know what horizontal is? Look at this. This horizontal is less. Now I've got to zoom in again.
Delete the pictures on the right and just drag the one
This
from the top left over.
horizontal is less than this horizontal.
You don't even have it centered, dude. You don't even have it centered.
Let's center it. Wait. Let's center it.
Shut the fuck up, Wesley.
Let's just center it. You know what? There we go.
Oh, Sav,
He's just here to waste your goddamn time.
Go away, man. Dude, you're going to talk over people, dude. Stop talking over people.
Is it not? Wesley, that's centered, is it not? Is that centered, Wesley?
No. It's off to the right. You can clearly see it. The top of the circle is to the right of your line.
What
are you talking about? You want it like that?
Yes, now pull the other one in.
It's already in.
Delete those circles and drag the other circle in.
It's already in.
What do you think it's going to do? It's just going to. It's the same, man.
It's exactly
the same picture, dude.
Let me get
delete those pictures. Delete those circles. All you have to do is delete those circles.
Why?
Walk them through it. Yeah. Show him how you did it. That's what he wants to see.
So he is a moron.
He is.
No question about it.
Says the guy who doesn't know calculus.
There we go.
Okay.
Oh, where's there we go. This is a circle. That is a circle. This vertical and horizontal is smaller than that vertical and horizontal.
Draw the circle on the top left.
He thinks it's different, guys. He thinks
it's fucking circle, man.
What a moron. Okay, let me just do this because our time is running out. How much minutes we got left, guys?
That's it.
On the subject, is it over?
Two, probably two.
Yeah. 2 minutes.
Oh, you're trying to run away.
You got 2 minutes on this.
No, we're on it.
Okay, there we go. Here we go. Copy, paste.
Yeah.
Look
at jobs and stuff.
What's going on here? Look at that. What's going on?
Difference. It's angular difference.
All right. I'll agree with you on that one. That's pretty good. You need I would say you need a solar filter.
Holy crap!
The other question on your experiment: do you have an experiment that proves that the Earth is flat?
Shape is not experiment.
There we go. There we go with the proof and the negative.
Science.
There
well,
you
no,
go.
You guys want experiments that prove
shape is not science.
Wesley,
you have to jump in.
Wesley.
90 degrees,
the
right?
Proof,
perpendicular.
The proof is required of a globe. Okay.
Why?
That's what you don't understand, because you have the positive claim that goes against observable reality. That's why.
So you don't claim it's flat then?
No, that's axiomatic. It's an observation.
No, it's not.
Yes, it
where,
is.
Where on earth is it flat? Where on earth is it flat?
Yes, it is.
Where on earth?
Do you observe
the level topographical plane? I'm not going to get into this game of semantics with you.
No, it's not. It's measurably not flat.
Listen, you little asshole. I'm not going to get into this. I'm not going to get into this game of semantics with you. Okay? You have a positive claim that goes against observable reality. You nor anyone else here, and I'm just going to keep talking over you. You nor anyone else here has a first-hand observation of a globe Earth. Therefore, the burden of proof lies with the positive claim, which is you.
So if we lived in a valley, we would think it's concave, right?
I'm not getting into semantics with you about it anymore until you have proof of your positive claim. The default observation remains.
It's not default.
Okay.
Yes,